Welcome my friends, welcome to my next lecture. Now in my last lecture I was talking about elementary analytic functions. In other words, I was kind of defined the notions of exponential functions or definitions of exponential functions in terms of Euler's formula. Then I have discussed couple of properties of exponential functions, and then I have kind of said that okay, so if it is a exponential, it's a map from complex plane to complex plane, okay, and so in the z plane if I take some sort of sets, say either say vertical line or horizontal line or say square, then what will be the corresponding image under these exponential functions in the w plane? And couple of properties I have discussed, and then I said that okay, there are more on I can talk about that. That means I have talked about exponential functions, so therefore it is expected can I have any other notions of trigonometric function like sine function, cosine functions, those kind of notions you know in real analysis. So my plan for today's lecture is to talk about more on trigonometric functions. That means I will explain, yes, you can define cosine functions, sine functions, hyperbolic functions in the context of complex plane or complex variable as well. So that I will start with those couple of properties, then I will talk about or I will define what is called log functions, then multivalued functions will come, then I will talk about branch and branch point, branch cut, these are the things, and later of course I will start the notions of what is called Riemann-Stieltjes integral, contour integrations, path independency and Cauchy-Green theorem. That is for the plan for the whole week 3, but today my plan is to talk about more on trigonometric functions. Okay, so as I said, so in my last lecture I have talked about exponential functions. Now you see, can I have any other trigonometric functions in complex setting as well? Okay, so this is okay, you can easily guess, yes, like what is the exponential functions? If you remember the definitions I have given, if z is equal to x plus iy, then I have defined e to the power z using what? Using Euler's formula. That means e to the power x times cosine y plus I sin y, right? That's what I have defined it. So therefore according to the formulas, if I take z is equal to just ix, so therefore your e to the power ix is cosine x plus I sin x, e to the power minus ix is cosine x minus I sin x, because of these definitions, the way I have defined my exponential functions. Then if I do some algebra, then it turns out that your cosine is nothing but e to the power ix plus e to the power minus ix divided by 2. You just add these two things, and if I take the subtractions, it turns out that your sine function is e to the power ix minus e to the power minus ix divided by 2i. So now this is the expression of cosine and sine where x is a real variable, but I want to define my sine and cosine functions if what will happen if I replace x by z variable. Okay, so same thing we will do. So motivated by the above identities, we define cosine and sine function for all complex number. That means I am just replacing x by a variable z. So that means the corresponding definitions I am saying that cosine z is nothing but e to the power iz plus e to the power minus iz divided by 2. That means I am replacing x by z. Similarly, here I am replacing x by z, I will have the definition of sine functions. So this is the corresponding trigonometric functions. So now sine function and cosine function, it's a map from C to C. So therefore sine is a map from C to C, z goes to sine of z, and what is sine of z? This is. Similarly, you will have the cosine functions. Now just by the definitions or from the definitions you can easily conclude that these are also analytic functions or entire functions, because I can write my cosine and sine in terms of the exponential functions, and exponential functions I have already discussed in my last class that these are entire functions or analytic functions in the whole complex plane. So therefore my sine function and cosine function, these are also analytic functions or entire functions on the whole complex plane, or analytic, or I should say analytic on the whole complex planes or entire functions, yes. Okay, so these are the properties, you can have it, like for example in the real case, if I have a sine function and cosine functions, what is the corresponding derivative of sine? So of course it is differentiable, and if I take the derivative of cosine functions, it will give minus of sine. If I take the derivative of sine functions, it will give you cosine of x. So this is for the real variable x, but similar sort of property is true in the case of complex case. That means if I have a complex valued function, that means cosine z and sine z, similar sort of properties what you are aware for sine function and cosine function in the real variable, same thing, almost all properties are true in the case of complex variable as well. Okay, for example, these are the corresponding derivative formula. So this is the corresponding identity, that means sine square z plus cosine square z is equal to 1. So I am not going to prove it. This is the properties of cosine and sine functions. So in other words, I have these definitions. If I use the definitions of cosine and sine, and do some algebra, and using the properties of exponential functions you will end up with all the nice properties. Whatever properties you know in case of real sine and cosine, that is also true for complex sine and cosine as well. So these are the two formulas which will be useful later. That means cosine and sine formula, cosine of z1 plus z2, which is cosine z1 cosine z2 minus sine z1 sine z2, sine of z1 plus z2 sine z1 cosine z2 plus cosine z1 sine z2. So these are also trigonometric formula you know in case of real variable as well. These are also periodic functions because exponential is a periodic functions, and I am writing cosine and sine in terms of the exponential functions. So therefore it is also periodic functions. So therefore it is a period is 2 pi, cosine of minus z is cosine of z, sine of minus z is minus of sine z. So that means whatever properties of sine and cosine functions you know in case of real variable, almost all properties are also true in case of complex variable, but one has to prove it. Okay, I have just listed down all the properties of sine and cosine functions, but you just use the definitions of sine and cosine in terms of exponential and use the properties of exponential, you will be able to prove all the properties. Okay, so I am not going to prove it, you just take it as an exercise and do that. Okay, but what is more important, this is the kind of major differences from your sine and cosine functions, what you are like familiar in the case of real. Like for example, exponential functions in real setting, of course it is an increasing function, it is unbounded, you know. But the major difference for the complex exponential is that it is periodic. Okay, that kind of phenomenon is not there in the real case. Similarly, sine function and cosine function in the real case, you know, these are the functions, nice, this is differentiable, all the properties of trigonometric properties are there, that is also fine. But one property you know, like sine and cosine function in the real setting, that they are bounded functions. Now I have a sine and cosine functions in complex variable. Compared to the real case, now this time you have sine and cosine functions, but these two functions are unbounded in the complex case. But that was not there in the case of real. Real case sine and cosine functions always bounded. Modulus of sine and cosine always dominated by 1, right? So this is you know. But however, in case of complex setting, the way I have defined in terms of exponential, you will see if I do some kind of algebra, I will prove that sine function and cosine functions in the complex variable, these are not bounded, these are actually unbounded functions. So I have given the proof. So look, so this is major differences from sine functions in real case from the sine function in the complex case. So sine function is an unbounded function in C. What is that? So sine, you know, I have defined it. So if z is equal to xy, you can have this formula. Now you can say that how do I get it? Now what is that? Sine z, right? So z is equal to x plus iy. Now sine, you have a formula, you already proved it, nah? So you use that formula, right? You use that one. Sine of z1 plus z2 sine z1 cosine z2 plus cosine z1 sine z2. So what will happen? Sine x cosine b plus cosine x sine b. Okay, iy. But this is same as sine x. This is actually cos hyperbolic y plus cosine of x sine hyperbolic y. And why is that? Because you just calculate cosine of iy. What is cosine of iy? What is cosine of z? Look, what is the definition of cosine of z? E to the iz plus e to the minus iz divided by 2. We just write it. E to the power iz plus e to the power minus iz divided by 2. Right? So what is that? This should be e to the power minus y plus e to the power y divided by 2. And this is the real case, you know. E to the power y plus e to the power minus y by 2 is nothing but cosine of hyperbolic y. Similarly, you can say that sine of iy, which is same as sine of hyperbolic y, just by the definitions. Okay, so therefore using the trigonometric formula I have just explained in my last slides, you can prove it that sine z, where z is equal to x plus iy, which is nothing but sine x cosine hyperbolic y plus I times cosine x sine hyperbolic y. Also you know this identity, sine square t plus cosine square t is equal to 1, cos hyperbolic square t minus sine hyperbolic square t is equal to 1 in the real case, you know. Then what I am trying to do is that I am going to estimate. So I want to show that sine z is an unbounded function. So what I will do, my aim is to say that sine z is dominated by some quantity. I will prove it, and I will show that this quantity blows up if z mod z approaches to infinity. Then this will also blow up. So that's my idea. So to do that, you will have just estimate absolute of sine z. Sine z formula is there. This is just square root of sine square x cosine hyperbolic square y plus cos square x plus sine hyperbolic square y. Then I have to use just corresponding trigonometric formula in the real setting, you know. This is same as this plus this, and which turns out that these are all identities. Okay, you do not need all the things, but for your understanding I am keeping it. But what I need is that modulus of sin z, if I do some kind of algebra, it turns out that this is exactly equal to this object. So in other words, if I take the square, that means sin z square, which is nothing but sin square x plus sin hyperbolic square y. So this is enough to talk about unboundedness of sin z. Why? Because you see, this is square is nothing but this plus this, and this is sum of two positive numbers. So therefore I can say that this will always implies that absolute of sin hyperbolic y, which is always dominated by modulus of sin z. That is the first one. It follows from here. Okay, and that's it. If I have that equality, then I am done. Then it says that, look, so now I am saying that, so modulus of sin z, which is greater or equal to some quantity. Now if mod z approaches to infinity, that means if I take x and y very large, that means what will happen, this object that you know in the real setting, that modulus of sin hyperbolic y, this actually blows up. That means this approaches to infinity if mod y approaches to infinity. Now if mod y approaches to infinity, that means mod z approaches to infinity. So that means mod z approaches to infinity, which implies, or you can say that mod y approaches to infinity, that means sin hyperbolic y approaches to infinity, which will implies that this is approaches to infinity if mod z approaches to infinity. So that means what? That means if mod z approaches to infinity, this is taking larger and larger value, so therefore it is actually unbounded. So to prove that, you just need to have this formula. That's it, and you have it. Because you have a complex number, you just calculate the mod, and what you have to do, you have to just use the classical trigonometric formula. That's it. And as long as you have this kind of estimate with the fact that modulus of y approaches to infinity implies that sin hyperbolic y, these values also blows up, implies that modulus of sin z approaches to infinity if mod z approaches to infinity. So therefore my sin function is an unbounded function. In the same way you can prove that cosine also is an unbounded function. Same trick. See, this time sin z has this kind of formula, you have to just use the cosine formula. Cosines of x plus y, cosine x times cosine iy minus sin x times sin of iy, then write it in terms of hyperbolic functions, then use the identity of trigonometric functions, and somehow you try to prove the estimate. Though I have written in my next slides that do the same process, so you just use cosine has this kind of expression, then if I kind of calculate the absolute, then it turns out that this is exactly equal to this one, which will implies this. The first one is enough. You do not care about the second one, because I just wanted to prove that it goes to infinity as mod z approaches to infinity. Now this is same trick. So if mod y approaches to infinity, that means modulus of sin hyperbolic y, it blows up. So it will implies that this is also approaches to infinity as mod z approaches to infinity. Okay. So therefore, unlike to the sine and cosine functions in the real case, this time I will have sine function and cosine function in the complex setting, but the major difference is that this time these functions are actually unbounded functions, and that you can easily guess, because I have written sine and cosines in terms of the exponential, that means e to the power ij, and z is of the form x plus iy, that means it somehow deals with the functions, well, it will have an imaginary part and real part. So imaginary part, if I take the modulus of the exponential, it will give you 1, it will not contribute anything, but the part where you have e to the power y, there you will have some kind of guessing that yes, if y approaches to infinity, e to the power y also approaches to infinity, and it should reflect on the behavior of your sine and cosine function, and that is exactly going on here. So in real case, sine and cosine functions are bounded functions, but in the complex case, these are two functions are unbounded. This is one of the major differences from real sine cosine to the complex sine cosine. So these are the again some zeros and some properties, as I said, like the properties you know in case of real, almost similar kind of properties is true. So okay, so if cosine of z is equal to 0, that means if z is equal to pi by 2 plus k pi, where k is an integer, so cosine z has the same number of zeros as its real counterpart cosine of x. Similarly, sin z is equal to 0 if and only if z is equal to k pi. Okay, so this will have what is called series expansions, because I can write cosine and sine in terms of exponential, and if I know the power series expansion of exponential, then we will have the expression of cosine and sine. This is the corresponding series expansions, and later on you will see when I will prove, I will introduce the notions of what is called power series, then I will show that the way I have defined cosine and sine in terms of exponential and exponential in terms of Euler's formula, all things becomes kind of equal. You do not worry like whether I am defining my sine cosine in terms of power series or in terms of exponential, where exponential I have defined in terms of Euler's formula or are equivalent. Okay, so note that I have written many more identities involving with the real functions cosine and sine can be proved in the setting of complex function sine and cosine as well. So there are many properties, so I have just listed few of them. Okay, again any other trigonometric functions like tan functions, cot functions, cosec functions, sine sec functions. So I have written the other trigonometric functions are also defined in the complex variable in terms of sine and cosines in accordance with the real definitions. So this is kind of real, you know. Similarly, you can have it what is called in the case of complex as well. So of course, the hyperbolic also you can define. The hyperbolic functions cosine and sine called the hyperbolic cosines and hyperbolic sine respectively. You can define cosine of hyperbolic z, it is e to the power z plus e to the minus z by 2. Similarly, sine hyperbolic z, it is e to the z minus e to the minus z by 2. So like in the real case, you have in terms of x, this time I am replacing x by z. Okay, clearly the functions cosine and sine are analytic everywhere because I am writing cosine and sine hyperbolic in terms of the exponential, and these are analytic functions in the whole complex plane. So therefore, you can these two functions are also what is called analytic functions, and reduced to the familiar hyperbolic functions, cosine function and sine functions if I replace z by x. So either you can say that you will have first definition in terms of the complex variable, then you take z is equal to x, it boils down to the real case, or you can think about that I have a cosine and sine hyperbolic function in terms of x, then I am just replacing x by z, and I will have the complex hyperbolic and complex sine hyperbolic and complex cosine hyperbolic. Okay, so similar kind of things you can do. Again I am just listing the properties, I am not going to prove it. So like the properties you know in the real settings, most of the properties are also true. For example, this is the identity cosine hyperbolic square z minus sine hyperbolic square z is equal to 1. So these are the properties, we just use the definitions. Cosine of hyperbolic iz is equal to cosine z, sine hyperbolic iz is I times sine z. So these are actually periodic. So these are the properties. So that means most of the properties that you know in case of real, you can have it. Okay. Similarly, you can have this kind of estimate. These are also unbounded functions. You can prove it from here itself. Okay. So like, so you can say that okay, cosine hyperbolic z is greater or equal to sine hyperbolic x, and this blows up as mod x approaches to infinity. So therefore, this is unbounded, this is unbounded. These are the zeros like in the sine and cosine functions. So you will have it. So okay. So most of the properties. Of course, sine and cosine function you know, also in the hyperbolic setting, these are the properties. Of course, I have just listed few of them, there could be many. Okay. Again, same thing in tan hyperbolic, cot hyperbolic, sec hyperbolic and cosec hyperbolic, you can also define in terms of sine hyperbolic and cosine hyperbolic. Okay, so now these are the kind of trigonometric functions. So I have defined exponential, then I talked about sine cosine, then sine hyperbolic, cosine hyperbolic, then like corresponding tan functions, cot function, sec function, cosec function, and corresponding hyperbolic functions. So now it is I am going to talk about what is called log function. This is one of the kind of you will see the classical log functions in the real case and the log functions in the complex. These two have a huge or major differences. Like this time you will see I can define my log functions, but this time it will be multi-valued functions, and then I have to somehow give out of multi-valued I have to extract a single valued functions. So therefore, from multi-valued to a single valued, and then the corresponding what is called branch will come. Okay, so now let me just, so this is the kind of the definitions you know in the log functions in the real case. In the complex case it will be entirely different. So let's see. Okay, so first of all you just recall how you define what is your in your log functions. So you have exponential functions. So you have exponential functions e to the power x, right? It is defined from r to positive real lines, okay, r plus, okay, not including 0. So then it is a injective functions, and I am defining log functions log x, which is actually r plus to r, which is the inverse of. That means it satisfies this kind of properties. Maybe I should say that ln x, that would be better to distinguish. Okay, so it is the inverse of the exponential. That means e to the power ln of x, it should satisfy this kind of properties. So that you know in case of real exponential, what is the real logarithm? This is nothing but the inverse of my exponential, right? But in case of complex, I will have the exponential function c to the power z, right? It is a map from where to where, c to c, okay? But I cannot just directly say that this function is inverse of that. But to talk about the inverse, I need my function should be what is called bijective. But we have already seen e to the power z is a periodic function, right? So therefore it is not a bijective function, it is not an injective function. So therefore I cannot just say, or I cannot define my log functions in the complex setting which is the inverse of exponential. It does not make any sense, because exponential functions in the complex exponential, it is a periodic functions. So therefore what I will do, I will define my log functions in a sense that it should satisfy this kind of properties. That means I will say that, okay, given, okay, somehow in terms of inverse, but inverse means I have to somehow restrict my exponential functions where it is injective, and there I will have the inverse, and then it perfectly makes sense, right? So therefore first I will see, or I will try to find out what are the complex number w such that if I have w such that e to the power w, okay, say w is equal to e to the power w, or say w I will define log of z such that e to the power w, that means e to the power log of z is exactly equal to z. So this kind of object, let's see. So if given a z, you have e to the power z, right? So I would like to find what are the w's you will have such that e to the power w is equal to z, they satisfies these equations. Means I would like to find the w's such that it satisfies this kind of equations, e to the power w is equal to z, and that w I will say that it is the kind of corresponding definition of my log functions, and this is actually parallel to the what is called my real case. Here actually your natural logarithm or real logarithm ln, which is nothing but the inverse, but here I cannot talk about the inverse, right? Because my function e to the power z, which is not injective, but at least try to find what are the w's you will have which satisfies the equations e to the power w is equal to z, and then see what kind of object it would be, and then I will talk about my what is my logarithm in the what is the definition of logarithm in case of complex case, and whether it will be a multivalued functions, then can I have a single valued functions, so on and so forth. Okay, so this is the definition. So that's how I will define logarithm functions, which I denote it as small log of z. What is that? Look, the logarithm was defined in an elementary algebra as the inverse of exponential functions. Okay, so that you know. Now we will follow the same idea defining the complex logarithm. Let me just say, okay, so first of all, since e to the power z is always non-zero, so therefore e to the power z is a map from C to, you can say that, C minus 0, because e to the power z image is always non-zero. So therefore, in some sense, if I want to talk about the logarithm, okay, so that means it should be a map from here to here. That means I cannot have the logarithm of for the point 0. So that's what I am trying to say. So since e to the z is always non-zero, so the number 0 has no logarithm. Okay, so thus for any z non-zero, the logarithm log of z is defined. I am saying that it is, say, small log of z is a root of the equation. So let me try to find out what are the w's satisfies e to the power w is equal to z, and that w I will say that it is the log of z. So that means if I fix a z, I will find what are the w satisfies the equations e to the power w is equal to z. I will say that log of z is nothing but that w. That's how I will define. Okay, so that means I am saying that w is equal to log z, so that it should satisfy these equations. So now you have a complex equations. So right hand side z is given, it is given, right? And I want to find what are the w's which satisfies these equations e to the power w is equal to z. Okay. So now if I take w is some form, say u plus iv, z is equal to, say, x plus iy. So that means let me see what will be the corresponding expression of w. So that exactly I have done it. Now to determine w in terms of z, because I will write that is the functions, that is the given z, the log of z is taking that values. So therefore I need to determine w in terms of z. So what I will do, I will have these equations, I will have to find w in terms of z. Now let w is equal to u plus iv, and let z is equal to r e to the power I theta, because z is fixed. Suppose corresponding exponential form is r e to the power I theta, where r is modulus of z, theta is the argument. And what is my w? W is equal to u plus iv. I would like to write my w in terms of z. Let's see. So you have e to the power w is equal to z. Then if I just do some algebra, so by definitions, if w is equal to u plus iv, then how I define e to the power w? This is e to the power u times e to the power iv. Okay, so that exactly this object. And right hand side you have a z, which is r e to the I theta. Now you have two complex number, so e to the power u, e to the power iv, which is exactly equal to r e to the power I theta. Now you have two complex number which are all both are of the form what is called exponential form. Now these two complex number equals what it will mean. That means your r is equal to e to the power u. So in other words, you can say that u is equal to ln of r. So this is real logarithm. And what is the relations between v and theta? So this is r e to the I theta and this is v. What is the relation? So v is equal to theta plus 2k pi, that you know, right? So therefore you have the expression u ln of r and you have the expression of v in terms of theta. So now if I combine it, then what will be your u plus iv? So your u plus iv, that means your w, which is u plus iv, what is that? U is equal to ln of r. What is r? If I take it r, what is r? R is equal to, you can say that modulus of z, na? Because z is equal to r e to the I theta. So therefore this is mod z. So therefore you have ln of mod z plus iv. What is v? V is equal to theta plus 2k pi. But what is theta? So this is ln of mod z plus I small r of z plus 2k pi. Correct? So therefore that's exactly I have written. So therefore then e to the power w is equal to z becomes these equations, which will implies the because I have two complex number, both are of the form exponential form, then you can equate these two complex number. It will give you u exactly equal to real logarithm of r. V is equal to theta plus 2k pi, where ln is the usual natural logarithm for positive real numbers, k is any integers. Simply I can write u is equal to ln of mod z, ln of r, and v is equal to what is called argument of z. Putting together what I will have it, okay. Okay, so actually this is small arc. So small arc you don't have to add it there, because this is actually your small arc. Okay, so now what I will obtain, that log of z, which is exactly equal to w, which is nothing but you can say that, I will write it. So I will write it. So this is exactly equal to ln of mod z plus I small arc of z. Now if you remember when I was talking about, in fact my initial lectures, that given a complex number, what is small arc of z? Small arc of z is nothing but, so theta, that one theta is running between minus pi to pi, that is means principal argument plus 2k pi. So this is exactly the one. So therefore this is w is equal to ln of mod z plus I small arc of z, and which is nothing but your log z. So now just solving the equations, then is what are the w satisfies the equations e to the power w is equal to z, given z is fixed, which is r e to the I theta. It turns out that your small log of z is that kind of expression. So given z, I am defining small log of z, which is the ln of mod z, that means that this is the real logarithm, plus I of small arc of z. Now from here you can easily conclude that since small arc of z, I already told you, given a complex number z, z goes to small arc of z. So then these kind of functions, okay, these functions are actually multivalued functions. So therefore small log, it has a small arc. So therefore I can say that z goes to small log of z, it is also a multivalued functions. Therefore it is expected if I replace by small arc by capital arc, I can make it single valued. So in general I can say that if I define my small log z given a complex number z, which is nothing but ln of mod z plus I times small arc of z for z is in c minus 0, in general small log of z is a multivalued functions, because small arc of z is a multivalued functions. Okay, so that now definition is clear. So definition is that given a z in the complex plane which is non-zero, and then I am defining my small log of z, which is real logarithm of mod z plus I of small argument of z. Now since small argument of z is a multivalued function, so therefore your small log of z is a multivalued functions. Okay, so that's my definitions of my log functions. Okay. Now that first observation is that small log of z is a multivalued function. So unlike the real logarithm, small log of z is a multivalued function because small arc of z is multivalued. So therefore, for example, I have given a couple of examples. For example, if I want to calculate small log of 1, what is that? Ln of mod 1 plus I argument of 1. But ln of mod 1, real logarithm, this is 0. Or what is the argument of 1? This is I times 2k pi. Okay, right? So you just write 1 as r e to the I theta form. It turns out that e to the power I theta, theta mean is 0, r is 1, so therefore it will give you actually I times 0 plus theta is actually 0 here. So 0 plus 2k pi, that means 2k pi I. So that means 1, so 1 goes to small log of 1, but small log of 1, it's a set, right? K runs over z, that means it is taking all those values. So 1 goes to this set. Similarly, if I calculate 1.001, do the same argument. So 1.001 goes to, this is actually, you can say that this is log of 1. this is actually log of 1.001. So therefore 1 goes to log 1 or 1.001 goes to log of 1.001, it's a set. So it's multivalued. Okay, similarly you can have this, just for your understanding I'm just calculating what 1 goes to log of 1, what is the value. Similarly you can have it. Okay, so look, the conclusion I am saying is that for each point z in C minus 0 is mapped to a set consisting of infinite number of values by the functions log z which differ from each other by multiple of 2 pi I. Yeah, it's quite clear, look at here. So therefore what is that? So this is actually small arg of z. So but small arg of z I can write, it is actually principal argument plus 2k pi, right? So therefore if I replace, if I write in this way, so therefore if I have z vary, so that means they will vary up to 2k pi. That's exactly I have written. So look, I have written. So for each it maps to a set consisting of infinite number of values of the function log z which differ from each other by a multiples of 2 pi I, and that is actually follows from the definitions. Therefore log of z is a multivalued functions. For example, 2 pi I means you can have just this one. So therefore minus 2 pi I, so one of the value, then I am adding 2 pi I, it becomes 0, then I am adding 2 pi I, it becomes 2 pi I. So that means it differs. So the set I am taking, it differs by 2 pi I. So in other words, what I am trying to say is that if I take any non-zero complex number corresponding small log of z, it's a set valued, it's a multivalued functions. And because of the fact that log of z, small log of z, I am writing in terms of small arg of z, and small arg of z I already told you that it is a what is called multivalued function. So therefore small log of z is a multivalued functions. Couple of identities, again the way I have discussed when I was talking about small arg of z, and there if you remember, I was talking about the equality of small arg of z1 z2 is equal to small arg of z1 plus small arg of z2. Similar way you can define it, because this time this is a multivalued function, this is a multivalued function, this is a multivalued function. So what is the meaning of this equality? That means if I take two elements from the multivalued functions, there exists another element from that multivalued set such that this equality is true. Okay, so you should interpret this equality in this way. So of course it is like in the classical case, you know, so therefore like log of x1 plus x2 is equal to log x1 plus log x2. So in the classical one, you know. Okay, so that kind of formula I was trying, or I am trying to interpret in the case of complex setting. So that means I am trying to say that, okay, if I have two complex numbers z1 z2, what is the meaning of small log of z1 z2? I am saying that this is follows the similar identity like in the real logarithm, that means log z1 plus log z2, but this time you have to be careful because these are multivalued functions. What is the meaning? Look, we must interpret the above two identities to mean that if particular values are assigned to any two of their terms, that means if I take one value from here or one value from here, then one can find a value in the third one such that this equation is satisfied. For example, I have written, so take z1 z2 is equal to minus 1, we select pi I to be the value of small log of z1 and small log of z2. So that means I am taking two values from small log of z1 and small log of z2. Then I am getting satisfied that if we use the particular value 2 pi I, which is small log of z1 times z2. Now z1 z2 is minus 1, so z1 z2 is equal to 1. That means I have a log 1. So there in the log 1 is a multivalued set. There 2 pi I sitting inside. So I am saying that if I take z1 is equal to minus 1, z2 is equal to minus 1, and if I take pi I from log z1 and pi I from log z2, that means I am taking pi I belongs to log of minus 1, pi I belongs to log of minus 1. This is a set, no? This is a set. Then I am saying that it will implies you have a 2 pi I belongs to log 1 because z1 times z2, because this is minus 1 times minus 1, such that 2 pi I is exactly equal to pi I plus pi I. So that's the way it should be meaning. Okay, because I am dealing with multivalued or set valued functions. So meaning of this equality in that sense, you just take two values from any two out of three sets, then there exists a value in the third set such that this equality becomes hold. Like in the small argument object I have explained. Okay, now the question is, I have a multivalued functions, so how to make it single valued function? So I have just drawn a diagram to make multivalued functions f into a single valued. Now for a point z in a domain of the definitions of functions f, choose only one value, say w, say from the set of values and assign. So this is a multivalued function, so let it be small f. Then out of this small f, I am so given z, small f is taking a set. So in the set, I would like to take only one value, so that I want to get from the multi-value to the single value. So I am saying that, okay, for given z, so choose a single value, that means I am defining is capital F, a single value w picked, that can be picked from the set f of z of value, so that, so I demand something. What is that? This single value function should be analytic. So that means I am not choosing randomly. So I have a multi-valued function. So given z, it maps to a set. From that, I'm trying to find a single valued functions with a demand that that single valued function should be analytic. That means I cannot just choose arbitrarily a point in the set just to make it single valued. No, I'm not doing that. I'm saying that you have a multi-valued functions to get a single valued functions, but I demand that you should choose single valued in such a way so that your function should be analytic. So that's I demand, I need it. So therefore log of z maps one goes to this one, or this goes to this one, I have already discussed. Now this is a guessed. How to pick values for a single valued function that is actually analytic. That means, and hence it is continuous. So that means I say that you have a small log functions which is multi-valued functions. How I can choose from this multi-valued function to a single valued function so that that single valued function is continuous or analytic. So that's kind of things I am doing. And now you can easily guess it. Okay, at least from the multi-valued functions you can easily say what will be the single valued functions, because your multi-valued function small log I can write in terms of small arg. So therefore if I replace small arg by capital arg, principal argument, that will be single valued functions. But the question is whether that single valued function is analytic or continuous. That is the questions we have it. Okay. Okay, so that's how it give you the definitions of what is called principal logarithm. Okay, maybe in my next lecture I will talk about that because it needs some ideas. Okay, so therefore, so what I have defined is that, so I talked about this lecture like trigonometric functions and various trigonometric functions that you are familiar with in the real setting, and also you can have the known concept in the case of complex case, but certain differences are there, like sine function, cosine function, that you know in case of real sine, cosine, these are bounded functions. However, in the complex case, these are unbounded. Couple of or many identities that you are familiar with, real sine, cosine and hyperbolic function, that is also true in case of what is called complex case as well. And then I define what is called log functions. So like you have a exponential functions, you have a log functions in the real setting. Now complex case we have exponential functions, then what will be the log functions I have talked about. And then the way I have defined it says that in general log of z, small log of z, it's a multi-valued functions. Now my next part is that from this multi-valued functions, how to get a single valued functions, but with that single valued functions, I need that it should have certain properties like analyticity, and that it will give you like what is called principal logarithm. So till now I have defined small log, then in my next lecture I will talk about what is called capital log, that means principal logarithm, that means a single valued functions, and I demand that it should have some kind of analyticity or continuity property. I think in the next lecture I will start with what is called principal logarithm. I think I should stop here. Thank you.